Hi everyone. So this is part 3 of this series wherein we are using the neural network, creating a neural network for FashionMNIST dataset. In the part 1 we have created 3 functions. One function to create the project directory, second to create data loader, the function that give us the trained data loader as well as the test data loader, and the third function that show us some sample images from the data loaders. And in the second video we saw that how to create a neural network, basically how to count the number of parameters in the neural network or trainable parameter. And in this one we will do the training and testing. So we will use these data loaders and use this neural network to we'll train this new neural network, and then we'll see the performance of this neural network also. Okay, so before we start this one, so we need to again run this code. So basically we call these functions called the project directory, and we know that this project directory gives us two variables, that is the home directory, and then the second one is the models path where we will store the our models. So home and models path. For this one we can call our get project directory, and we have home and models path, and then we need data loaders. We can just call the train data loader, declare the train data loader and test data loader, and we can call a function called create loader. So this has created the loader for us, and if we want to see some sample images we can call a show sample, and we can pass the train data loader. Okay, so we have the train data loader images from this one, so it means these two methods are working fine. Okay, so next is to get the neural network. So we can get the model, and we can call our this class neural network. So we have this model for this. Okay, so we have everything essential that is required to train. These are the three things that first we need, and before we also need some hyperparameters, and we know that we need a batch size, and batch size we can pass into the data loader also. So batch size, for example, we can say the batch size is 64, and the learning rate, we'll see what is the learning rate. So learning rate is, for example, we can say 0.01, and then we need the box, how many iterations we are going to have. Let's say we want 10 iterations for the time being, and we run this one, and we can pass this batch size here also, so that the create data loader works perfectly synced with this one, the batch size that we have declared. Okay, otherwise it will take default and it will not, this variable will not be reflected. Okay, so here we have model, and now we need to move to more functions. One to calculate the loss, and to optimize one optimizer. Okay, so we can call this function as a loss function. Loss function is equal to, let's say we are using the cross entropy, and then cross entropy loss, and this is our loss function. And then we need optimizer. Let's say we are in stochastic gradient descent optimizer, and we can name it as, we call the torch dot optim dot sdt. And then in this one we need to pass the model parameter, because these weights are the thing that we need to optimize. We want to update the weight so that our neural network is trained. So we'll see all of these meaning of this soon, but for the time being we'll just pass the model dot parameters. And so this SGT will update the model parameters, but how should these parameters be updated? It depends on the learning rate, whether you are going to subtract the gradients or just a part of only you want to take small steps. So basically what we'll do, we want to supply the learning rate, so that not we don't want to update all of the model parameters in one go. We want to take one step at a time, and very small steps. So we can say the learning rate is 1 minus 3. Okay, next what we need is device where we are going to train, and in case we have the CUDA on our device, so we say the device is CUDA, otherwise we use the CPU. So CUDA if torch is available as CPU. Okay, yeah, that's it. So these are the things that we need for the training. Let's start first doing the one batch only. We will write the training method later on, but let's start only for the one batch. And how to get the one batch? One batch we can just get the from the train data loader. We can convert this to an iterator, our train data loader, and then we can get the next. We can call the next method on the top of this one, and this will give us our first batch. So the shape of the X will be 64, 1, 28, 28, and Y will be 64. Okay, so now what we want to do is we will pass this X to the model, and this will call its forward pass. So what will happen is we know that when we created the neural network, we give if the model is expecting the 28 by 28 image, that is 784 pixels, so it will first flatten. It will call the first flatten function. It will convert to the 784 values, 64 by 784, and then it will go to the first layer. It will convert that 784 into 512, and then it will convert to 512 to 512. It will call the ReLU function in between, the activation function, and at the end it will give us the 10 neurons. At the output level we have the 10 neurons. So basically the output will be 10. So the model X should be 64 by 10. Why 64? There are 64 images, and the 10 is the output numbers that it should give. So you can call this as numbers as the Y predicted or predicteds. Okay, just to show that is okay. Okay, so we can check this one. Print Y predicts dot shape. Okay, so this is 64 by 10. Okay, so now what we want is that, because this is a Y predicted, so it shows us 10 number. Let me show you that how does these 10 numbers look like. Y predicted. Let's say we want to print 0th number. Okay, so this is the 0th, and these are the 10 numbers. But what we are interested here is at the first go that it says that for the first image these are the 10 numbers, and whatever is the maximum we will say that is the predicted class. So we want to find out which one is the maximum. We are not interested in what number it is, whether it is 0.08 or 0.0805. We are not interested in actual numbers. We are just interested in which index has the maximum number. So whichever index has the maximum number, we'll call that as the class. So for example, if we can call this as we want to find out which maximum number it is, so we can call torch.max, and we can pass this as Y predicted 0. It says that this is the maximum number, 0.0897. So this is the last number. So this is the 9th class. So 9th class means the 9th is the index which is the largest, and from this one we know the 9th represents the ankle boot. So it means that this image, according to this model, which is still untrained, is the ankle boot. So we are interested in this number only, which index has the maximum value. And second one we are interested is, for the purpose of training, we want to compute the loss, because sometimes it is the 9th, it may be the correct class, or it may not be the correct class. So we want to compute that difference. We want something that can actually tell us that how far we are from the correct class. For example, if our y is the correct class, so if we see that y0, let's see what is y0 actually. So y0 is 8. So actual image is this one, but our predicted is saying, y predicted 0 is saying that this is the one. So there is a difference between these two, but we can see the difference is not very big. So if the difference is not very big, so the loss should be less. But if the difference is very big, then the loss should be high. So and that loss can be computed by the this function that we have declared, NN cross entropy loss. So NN cross entropy loss gives us a number that tells us that how far you are from the correct class. So in case predicted class is this one and the actual class is this one, so this is negative and this is positive number, and they are quite far from each other, so then we assume that NN cross entropy loss should be on a higher side, and so that we know that we can measure the performance of the network using the loss only. Okay, so let's take one example here instead of doing everything from this one. Okay, so let's take one hypothetical example. This is what we want to do in the training method, that we want to compute the correct index, we want to compute the correct accuracy, and we want to compute the loss. Okay, so let me create numbers here, a matrix here. Let me say A is equal to A is a matrix, and we can call that as np.arange. Yes. And this is the A range, means that this is a number from 0 to 5, and what we can do is I can create to reshape, and reshape, let's put it into 2 by 3. So now it is a matrix of 2 by 3. So from this one we want to find out which, this is a matrix, so you can assume that this 0, 1, 2 are these are 3 numbers, but in our case we have 10 numbers. So we are not just having the only one model, one output, but we have 64 outputs like that. So we have to compute the loss for all of the 64. And similarly, we have to compute the maximum index, not from the one, but for all of the 64. And then we want to compute the total loss of this batch. We want to compute the total accuracy for this batch. We want to compare with the actual Y. This is the Y true. Actual Y or targeted Y or Y true, you can write anything. So we want to compare whether this is matches with the predicted or not, and how many matches are there. So that is our batch accuracy. And once we do the we complete this training for all the data set, then we know that in this epoch that's our accuracy. Okay, so this is our A. So now we want to find out the first is the maximum. So 0, 1, 2, you can assume that these are the output from the model for the first image, and 3, 4, 5 is the output for the second image. So what we want is that we want maximum from this one and maximum from this one. Okay, so if we are assuming there are 2 images and each output layer has only 3 nodes. Of course we can make it 10 also, but just for simplicity, so that we can concentrate on this one, how does it work. So that's why I have created just 3 only. So our objective is that we should, because we know that this 2 is the maximum for the first image and the 5 is the maximum for the second image. So what we want is our output should be 1 and 1. That's what we want. We expect that maximum function, so we need a one maximum like this one only. Okay, so we have a function called, this is a numpy, so we can call numpy argmax. So we can call as argmax, np.argmax, and we can pass it to the A, and it gives us 5. Okay, so what does it mean, that why it is giving 5? So argmax by default, if you do not pass any access variable, so it assumes that there are no hierarchy here. This is all flat numbers, and out of these flat numbers, this is 0, this is 0th index, this is first, this is second, this is third, this is fourth, and fifth. The fifth index is the fifth one is the highest, so it returns the 5. So argmax gives the index of the highest element, but assuming that everything is flat. And once we pass the x is equal to 0, is equal to 0. Let's say we pass x is equal to 0. Now what will happen is it gives 1, 1, 1. So now it is giving that from 0 to 3, the maximum is 3. From 1 to 4, maximum is 4. And from 2 to 5, maximum is 5. So the index of 3 is 1, index of 4 is 1, index of 5 is 1. So basically it is giving you from the column side. So this also we don't want. So what we want here is access is equal to 1. 2, 2. Yeah, this is what we want, that from 0, 1, 2, second index is the highest, and from 3, 4, 5, second index is the highest. So we will be using, whenever we want to compute the maximum of our numbers from the Y predicted, because we want to compute the Y predicted, maximum Y predicted is 64 by 10 images. And from this one, 64 by 10 tensor, so what we want is that from these 10 which one is the maximum, then for second 10 which one is the maximum. Okay, so this is 0 1 2 3 4 like this one, so which one is maximum like this one, and then which one is maximum like this one. So this will give us 64 numbers. And similarly here it is giving us, it is 2 by 3, it is giving us 2 numbers. When it will be 64 by 10, it will give us 64 numbers. So this is what we want. Okay, so this should be okay. And our next task is to compute the loss. And now how to compute the loss? For that one, let's create a predicted some list. Let's say our numbers are 0.4, 0.1, 0.01 and minus 0.2. So this is the predicted, and these are the predicted numbers. So right now I have taken only 4 numbers, but in actually these are the 10 numbers. Okay, and let's say this is one batch. I just added so that it reflects the way that we process the data. So predicted is one batch, and we may have another batch. We will see an example. So where we'll add, if we have 2 images, then we'll just say the predict comma predict. So we'll pack all those numbers. Okay, so and we need to convert this predicted to the torch tensor also, so that we can easily we are doing whatever we will do in the train method. Okay, so this is a torch.tensor, and we can pass this predicted to here, and we can give the data type of this tensor also. The d type is equal to torch.flavor. Okay, so this is our predicted. This is a tensor with these numbers. Okay, so now what we want is, let's say our target is target number is 0. So what do you mean by target here? So target means that its actual class is 0. So actual class is 0. Actual class means this y. So target is 0. Y target is 0. But we don't know from looking at this list, we can easily find out the maximum here. This 0.4 is the maximum. So if we find out the maximum here, the argmax, so it will give us 0 also. So 0 and 0, since these two number matches, so the loss should be low. Okay, so let's compute this one. So but before we compute, what we need to do is we also need to convert this to a batch of image. Okay, just say target. Okay, and then we also need to convert this target also to the tensor. When we do the training, everything already will be in the tensors. We don't have to worry about it. Since this is an example dataset, so we need to convert manually to the torch.tensor. So you can see target, and in this one, so this is a target, so our d type will be the long torch. Okay, so this is our target, and if you see this our y0, this will be also of the same shape tensor. Okay, so I'm just creating as we have the data set. So we'll have a data set like this one. So we have a predicted, which is of the 10 numbers. Here we have 4 for a float data type, and the target will be long data type. So now how to compute the loss? So in order to compute the loss, we have already declared the function called loss function, and then cause entropy loss. So we can just call this function to compute the loss. So I can say loss function, we can pass the numbers over that we have predicted this one, and our target is this one. Okay, so it is 1.0874. Okay, now let's see, copying it to another cell, and let's see if we have instead of 0, let's see 0 1 2 3, and let's say our target is 3. Now, when we say the target is 3, what does it mean? Our target is 3, but the predicted you can't change. Predicted is always the maximum index. So whatever is the maximum, we'll say that that is the predicted, and target depends on the true value. So we say so now if the target is 3, earlier loss was 1.074. So I think you know that now if the target is 3, and the predicted is 0, so it is a difference between that, and that is also on the negative side of this one, so the loss should be high. So when we compute this one, so we can see that from 1.08 the loss has increased to 1.6874, and if the target is this one, so it will be somewhere between 1.08 and 1.674. So let's say our target is 1, so it is 1.3874, and similarly if the target is 2, it will be more close to this one, higher than this one, but this is more close to this one. So depending on how far you are from the maximum, so the idea is that neural network should be trained that it gives you the maximum index, so maximum value for the right index. So if your target is 2, so it means that we want to update our weight so that index the value at the second index is maximum. If the target is 3, then when neural network should be trained so that the value at the third index should be maximum. And how to train this neural network, how to change those weights is the magic behind the optimizer. So that's why we have given the learning rate and the model parameters. So the optimizer will compute the gradients, and then it will update the weights according to your learning rate. Small changes will be there, and after a number of epochs we will see that the performance has increased. Okay, so that's the idea behind this one. So now I think we can write our train function now, and we'll write train method for only one epoch, and then we'll call it for number of epochs. So that is our train definition train, and this train will accept the data loader. So we'll have we'll pass the train data loader to this. We'll pass the model, because when we pass the model, we'll give them all the parameters also. And we need to pass the loss function, that which loss function we are using. There are so many loss functions, so that you can change your loss functions also. And then we need the optimizer. So these are the 4 things that a train method needs. Okay, so let's first compute the number of batches, that how many batches. It's not required, but in order to compute the loss and everything, we need how many batches are there. Okay. But per se we don't need for the training purpose, it's just for to compute that what's happening inside the, we need that. So number of batches, want to find out the number of batches, is just nothing but the length of data loader. So we got the number of batches, and how many images are there. We know it says 60,000 images, but we need to compute from the data loader. And in order to, if you want to compute the images, then also you can compute the data loader, but not from the data loader, but data loader dot dataset. Okay. So let's say we want to verify that it's working fine or not. Number of batches and the size, and we can call it here train, and we need to pass to the train data loader. Then we need to pass the model, loss function, and optimize. We have everything declared already. Okay, so we have 938 images and 60,000 data set of the image size. Okay, so now is our step to start the training. And before we start our training, we need to transfer the dataset as well as model to the device. So if CUDA is available, so it will go to the CUDA device, otherwise it will go to the CPU. Okay, so we can say that model is equal to model dot, we can jump for model, we don't need, we can just say model dot to device. Okay, so model dot to device will go to the model, and whenever we are training, so we need to call the train function, model dot train. Okay, so if we are in the testing mode, then we will call model dot eval mode. So if we are going to train, so we will call this model dot train. And what we need is now we will initialize, because we want to also compute what's happening in the training. So we want loss to be calculated, as well as how many we want to compute the accuracy also. But since we will do in a batch side, this is a mini batch, we are taking 64 images at one go, and then we need a lot of images. We'll process lot of batches inside that. If this train function will assume that you will process the complete data set, but in many batches. Okay, so for that we can call we can initialize some variable here. That's the batch loss and batch accuracy, you can say, or batch correct or total correct. How many correct we have. If we know the correct images, we can easily find out that the accuracy from the total. We know the size here, that how many images are there, how many to correct are there, so we can find out the percentage. And from the batch loss, we can find out that if we want to find out the total loss, we can find out from the these are the number of batches, and that's the total batch loss. So in one batch loss, what's the loss per batch, we can find out. Okay, so we'll keep adding all of the batch loss, and then we'll divide with the number of batches. And similarly, we'll keep adding the total correct, and we'll divide with the size to find out, or multiply with 100 to find out the proper percentage accuracy. Okay, so we can initialize this as 0.0 to 0. Okay, so this is what we want, total correct and batch accuracy. So now we can write a loop here for, and we can call an enumerate for batch, that is the batch ID basically, and this will return us x and y, because as we saw that next idea gives us x and y, so similar with this one. So we can call enumerate, and in this one we are calling a function called tqdm. It will give us a nice progress bar. It's not required. It will just show you what percentage of data has already been processed. So we're calling it as a data loader that we receive from the train. Okay, so this is what we'll have to do. And now is the time to process, and we need to, because model is at the device now, and we need to transfer x and y also to the device. So you can say that x and y is equal to x dot to device. So now the x and y are also at the device, at the same device, otherwise there will be an error. Okay, so now both are at the device, and this y is nothing but, we know that this y is the y true, and y we will get from the model is the predicted. So I can call it as predicted. Predicted is equal to model and x. So we give x to the model, and this gives us predicted. Now we got the predicted values. This will be 64 by 10, and then we want to compute the loss. So loss is equal to loss function, and in this loss function we want to give the predicted and the y. So this is the loss for this particular batch of all the 64 images, and this loss will be a scalar quantity. We can convert dot item to convert the actual value for this one. Okay, so this is the we can call that is as a, we can write this is a prediction error, or prediction error, because this loss is the prediction error. If there is some loss which is high, so that is the prediction error. Next is the back propagation, because we have computed the loss, and what we want to do is in our next batch we will update our model parameters so that at every epoch, every step, this loss gets reduced. And for that one, for back propagation, first is that you need to call the optimizer and call the zero grad. So any gradient that are, because gradients are always accumulated, so what we need is we need to call a function called zero grad, so that will make all of the gradient function gradient to the zero, so it doesn't affect the previous batch, and we'll already update the model parameters. Okay, so this is optimizer.zeroGrad, and then loss.backward. So we will compute the loss.backward, so it will compute the gradient. So it will just initialize the optimizer so that there are no gradients from the previous step. Loss.backward will compute the gradients, and then we need to call the optimizer.step. Optimizer.step will update the model parameters in the direction such that the objective is that your output should match your targeted output. Okay, so this is done in the backpropagation. Next is computing all the statistics. So we have already a loss. So what we will do is this batch loss, we can say the batch loss plus equal to this loss. So we'll just add, since it is a tensor and this is in scalar quantity, so what we'll do is we'll call loss.item. Okay, so loss.item, we are adding it to the batch loss. So our batch loss has been updated. Next is that what we want is to compute the how many correct values are there. So as we saw that we want to find out from the argument argmax. Okay, so for that one we will say that correct, how many correct are there. So correct is can be find out. We have the predicted values. These are the predicted by model, and on this one we will call the argmax. Okay, so we can call the argmax and we can pass that x is equal to 1. So predicted is a tensor, torch tensor, and we can call a method argmax on this one. So it will give us argument of the maximum index by x is equal to 1, as we saw earlier, and then it will give us the maximum, and then this maximum can be compared with the y. So this y is our true values. When we say equals to y, so this number will be 1 or 0, just 1 or 0. Why? Because it will give some number, and this equality will compare with this y, and if these both are equal, it will become 1, otherwise it will become 0. Okay, so this is what is the correct. So correct so far correct is equal to just 1010. You can say a tensor of 1010. Okay, so now what we want to do is we want to take the we want to add all of these correct, so that we know that these are the numbers here. Okay, so correct is equal to, we can say the correct dot sum. So we have added, so 0 will have no effect, only the number of ones will be added. So once we add these numbers, so it will again become a scalar quantity, and since it is a scalar quantity, so we can call the item function here one-dimensional tensor. So one-dimensional tensor, so we can call this an item, so it will convert this correct to the scalar quantity. And now our task is that this correct should be added to this total correct, because we get the total number of corrects in all of the images. So far we have only one batch, and we will see here that total correct is plus equal to correct. Okay, so once it is done, so outside this loop we are interested only in two numbers. What is the batch loss and what is your total correct from this one epoch, so that when we are doing more than 10 epochs or maybe 100 epochs, we know that the model is getting trained. Otherwise there is no point in spending the computation time. Okay, so now what we will do is we will divide this total correct with the what number, just divided by the size. So total correct is based on the number of images. So out of 60,000, how many? So we just divide it. So that's the fraction of the images may be the correct. Okay, and then from the batch loss, what we need is batch loss will be divided with the number of batches. So once we divide it with the number of batches, we know that per batch this is the loss. Okay, because different data sets may have different batches. So what we are computing is from 64 images what is the loss. Or if you want, you can further divide it by 64 to find out the batch loss per image. Okay, and now you can print these numbers, that this is the total correct loss of this is our accuracy. And if you want to print it, then you can just say print. You can say that our accuracy, and remember this is a train accuracy, so we can write it as a train accuracy. So train accuracy is equal to from how to get total correct. So the total correct needs to be converted to just fractions. You can just write it as 0.1%. So it will convert it to the one decimal, and in terms of percentage. So we'll multiply by 100. Okay, so this is our total correct, and similarly if we want to display the loss, we can say that total loss. So this is the total loss. Total loss is the, you can say, the batch loss. Okay, so this will print, and we need to, if we want, we can return also, but if in case we want to do that, we should be okay. Okay, so let's run this function. This is the TQDM. We are getting the progress bar, and it will print. The train accuracy is 26.60, and loss is this. It's pretty much big, so we can just say that 0.3. Just showing the 3 decimal places. Now we'll see that we have run, and this is 26%, and now it will run again. We'll see whether it's getting improved or not. If it's getting improved, then it's better. Say it's 44% now running second time, and loss is so the objective is that this optimizer should work. That, gradients are being computed, and your model parameters are being updated in a way that your loss is getting reduced and number of corrects are increasing. So that's the whole objective of the train data loader. Okay, so I will call this one now. Okay, so our train data loader is working fine. So next is the evaluate. We want to write a method called test. Okay. So now in the test function, when we want to do this, so we want to call first the model.eval. I'm just writing soon. So these are the two things that we want to do. First is we need to call the model.eval, and then when we call this torch. Anything that we do in the testing should be under this one, with torch dot no grad. So no gradients to be computed, and everything whatever you write will be under this one. So these are the things that you need to remember. Always call model.eval and torch.no gradient. Otherwise there may be a problem that gradients will be computed, and we don't want to update the model weights during the, because we know that this will whenever we call this, models will be weights will be updated, and it needs a computation. There is a computation time also, and and at the test time we don't want the models weights to be updated. So that's why we're saying no gradients to be computed. But we still want to compute the loss at the end. So if that loss is at some 2.0, then what happens when the model sees the unseen data? So training data is model already know, and that our weights are optimized based on that data. Now the test data is model has not seen. So we want to check the performance of the model. So what we'll do is we'll write a function called test now, and test will also take the data loader we know, and in this case our data loader will be the test data loader. We still need the model, and we need a loss function that we want to compute. Okay, so we don't need optimizer here, and our most of the code will remain same. You still need to compute this number of batches. You still need to compute the size, and then we need, instead of model.train, now we'll call model.eval, evaluate. So this is our model.eval, and we still need the same thing. I can just copy it from here. Model.eval is here. So model.eval is here, and batch loss total correct is correct. TQDM data loader is okay. XY is okay. This is okay. This is okay. Now we don't need back propagation. There is no optimizer here. Okay, rest all is same. So we have, and one more thing that we need to do is we always forget it. That's why I write it separately. That everything should be under with torch.no grad. Okay, so I can write this method here, this code here, that with torch.no grad, and we can indent this one. That's it. Okay, so with torch no gradient, do the same thing. Okay, and the it will print, and we can say that this is our test accuracy. The total loss is test loss. Test loss, we can call this as a train loss. Okay, so now we can try how the test is working. Okay, so let's see this test now. So instead of data loader, we need to call the test data loader. So this is the test data loader, model and loss function. Test data loader. And we need to see this is the test data. Okay, so our accuracy is now 51%, and the total loss is performing very well on the test data sets. Okay, so we are ready with the train and test. Okay, I'll just refresh everything so that everything is cleared out. There's no training right now, so we have only the two methods written, train and test. And now we'll start the training process. We know that our epochs is 10. So we have, I think, already defined in our hyperparameters that we will be training it for epochs 10. So what I'm going to do is write a for loop here, in which we will call, first we will call the train, and then we will call the test. So let's say for t in range epochs, so t is our timestamp, call e whatever, so t is timestamp, and we can say the print epoch. So this is basically t+1. So this will tell us which epoch we are currently in. /n, we can just say just print a line here. So this is our first epoch, and in this one we will call the train function, and we will give this train data loader, and next step we want to give is the model, and then we want to give the loss function, and then we want to give the optimizer, and then we will call the test. In the test we will pass the test data loader, we will give the model, we will give the loss function. Okay, that's it. That was our task. Okay, so let's see what happens in the when we do the training for the 10 epochs. What happens? So this is our epoch 1. It should be something around 26%, training 34%. It will keep on changing, and you can see the test accuracy is 47%. Training is getting improved from 34 to 54. Test also gets improved 54 to 57.8. It's getting improved by 4%. Loss is getting reduced 58 to 62. This is our epoch 4. So you can see that our accuracy is getting improved 62 to 65. Now they are close, so 66, 65, so now both will be close, but loss is getting reduced 67. So we have a in this neural network is very small network, so we don't have many layer, very deep network. We have just used 2 layers only, one input layer and then 2 other layers. So we are able to reach up to 70% accuracy. So we started at 34%, and we have reached up to 71% in 10 epochs only. So remember, we can still try more for 20, 50, 100. It may possible that your accuracy is getting improved. We may try with different optimizer functions. We may try some different batch size. We may try different learning rate. But there are so many other things to tune the hyperparameters. So this is how the neural network is trained. Our next task is to save this model, because what will happen is sometimes we are not training continuously, so we want to stop the model and we want to ensure that model is saved, and we can start from that point also, or checkpoint. Okay, so in order to save the model, we already have the models directory. So remember that we created the project directory that gives us the models path. So here I'm going to store the model. So we already have the model's path. So what we need is we just need to call the torch dot save, and in this one torch, when we want to save the model, we need to pass a model state dictionary. You can create a dictionary also, that you can save the dictionary, or at the minimum we need to call model dot state dictionary. State dictionary. So that is the state dictionary, contains all of the parameters, and you need to pass the model path. So basically now model path is a directory, but you need to give a file where do you want to store the save directory, this model state directory dictionary. So for this one, what we can do is we can create a model path. So we have the models path. We can create a variable called model path, which is basically voice.path.join. We can give the models path, and plus we can give some name to this one. Let's say I'm giving model.pth. Okay, and this model path, so this is a file under models path, and this name we need to pass this in here. So once you run this one, so this model is saved now. Okay, so since this model has been saved, so it means that this model can be retrieved anytime and we can do the testing. Okay, so far we have seen that our testing accuracy is 71%, but now let's try to load this model from this path, and then we'll check dictionary. If it loaded correctly, then it will give us close to 71% accuracy, but if it is the default model, it will not give us 71% accuracy. It may give us just about initial accuracy, which is maybe 40% or 5%. Okay, so now how to load this model. So we have already saved this model. You can go to this directory models path and see that there will be a file model.pth. Okay, so now loading model. So let's say create first the model is equal to torch neural network. So this is our neural network. So this is created. So this is now a default model that's coming from the neural network. So we don't have the model now. Okay. So now what I will do is you call this function model dot load state dictionary. Load state dictionary, and in this load state dictionary we need to call torch.load. Torch.load. So first we'll load this model from the models path, and we need to pass this model path. So what we're doing is that this model is loaded into this torch.load first, and from this one its state dictionary is loaded into the model. So that's the only thing that we need here. Okay, so all keys match successfully. So it means that we have been successful in loading the model. And now what we want to do is we just need to call the test. So without any training, we just need to call the test. So test, and we'll pass this model, and we'll pass this model, and then what next we need to pass is test data loader. So test data loader model, and then the loss function. So this is the loss function. Okay, so it is giving us the 71% accuracy. So we have the fresh model downloaded from the we may download it from some other cloud repository. Also, there are so many models available, and we can just upload the model and run it on your dataset. So that's what it does. So now if you want to use for the CPU also, you can also because most of the time what will happen is that you have the model trained by someone on the CPU, and you want to test the model on the CPU also. That's perfectly okay. The only thing that you want to write is that this model to be transferred to the CPU, and let's do that. Okay, let's say that we want model is equal to model dot, we need to just set device is equal to CPU. So device is equal to CPU by default. Okay, so now device is model dot CPU, and when we call this function called not test this one. So it's still working same fine. The device is in CPU, so it will automatically, because we have written a test function like that only, that in the test this model will go to the device. So since the device is CPU, now it will go to the CPU. If you want, you can display also here. Let's say if I want to write what's the device here, it is here. Device, just to verify that it is accepting device test, is accepting device as a CPU. Okay, so it's taking CPU device. So it's taking CPU device and the whole code is running on the CPU. So it doesn't matter whether you have trained model on the GPU or whether you have trained model on the CPU. Okay, so that was all about this one. So maybe last thing that you can do is that sometimes you only want to test only for a single image. So this is okay. The test data load is working fine for the whole data set. We have achieved the test accuracy, but when we want to deploy this model, so we just want to test only for a single image given by the user. So for example, if you have a mobile app and you want to give output to the user, then you want to try it only for a single image. So for the single image, what we'll do is, let's get one image only, and in order to get the one image, we just need to call the next ITR and our test data. Okay, so this is our X in and Y is the single image. I can just say XY is equal to X0 and this is 0. Okay, so now X and Y are single images only. And we can check it X dot shape, X dot shape and Y dot shape. So it is 120/28 and top size. It's not written because there is no shape here, so just use it. Okay, so tensor 6 is the 6 image with the 6 label is the its actual value, and its X is 120/28. So what we want is, so whenever an image will be read, it will be of this shape. So what we want to check is what is the predicted value for this one. Okay, so since we have only one image and we want to find out only class for this image only, correct label for this image only. So what we need to do is, we will first transfer this model. Let's call this model. We have this model.neural network. So if you have, for example, you may use Flask to deploy the model, that's what you need to do. That you will call a neural network. You will load the state dictionary. Okay, so the model has been loaded, and then you need to transfer this device is your CPU. Okay, so you will not call the one data loader, so you don't need that data loader. What you can do is, you can just say that model dot to device. Okay, test function is for the whole data set, so we will just do it for single image only. So model is to CPU, one image can be tested on the CPU. Okay, and then we need to use that with torch no grad. Okay, so with the torch no gradient, and what we want here is that we will process the X, which is in 128 to the model. Okay, so we'll say the predicted is equal to model and X. Okay, let's say whether it's working fine or not. We'll check whether we are getting some predictions or not. Okay, so we are getting some prediction for 10 numbers. Next task is for us is to, now here we don't we're not interested in loss even, because we have only one image. Whatever the loss will be, we know that this is minimum because we have trained this data set, we have trained this model, so that part already know. What we want to communicate to the user is what is the maximum number, not maximum number, but what's the maximum index for this one class. We know that we can find out that maximum using the .argmax. Okay, so what we can do is predicted is equal to predicted.argmax and we can find out maybe here it is. It doesn't matter even axis also, because we have only one axis only. It's not much here to do. You can assume this as a flat number also. You can give axis equal to 0 also. It's, in fact, it's single. Okay. You can print it here that these are the predicted numbers, and 4 is the maximum. We can count it 0, 1, 2, 3, 4. This is 57.71. So we can see that this is actually the maximum. So it is giving us the maximum number. So this is what we need to do for the testing. So this is the predicted class is 4, and we don't know whether what is the true class. So, okay. So but we know this is true class is 6 actually. So model is not correct for this case. So let's see, we see next batch. So this batch is 9, and let's see what model says. Yeah, and this image is correct. So this is an actual label is also 9, and this our predicted label is also 9. Okay, next is that we want to display these images. You said 9, I said 9, so it matches. Okay, so for this one, what you can do is you can just find out the to display. We can image. We already have this image. Only thing is that this is in the tensor, so it doesn't matter. So let's say the plot dot show x show. So yeah, we need to convert, we need to unsqueeze it, because this is 128, 128, so we need to unsqueeze this one. Squeeze. Okay. And then we need to pass this as a CMap is equal to gray. So just see the semicolon. Okay, so this is the image that we used it for the prediction, and we know that target y is the tensor 9, and if you want to see that what image this is, so we need to call this as a y.item. This will give us the 9, and we can call this as a true, or we can call it as y true. Y true is y9, and then we can find out this true basically from the label. So we can call their labels y true. Okay, so this is the y true, and similarly the target one. So we have the predicted. Similarly, we can also call y predicted. Y predicted is equal to predicted dot item. So this is also will give us the 9 hopefully, and then we can call this same thing. We can call as y predicted is equal to labels y predicted. So this will give us the actual string associated with the predicted labels, and once we have the actual string, we can show it in the plot dot title. Okay, so in this one we can say that true value true is equal to y true. So predicted is equal to so it says true is enkelboot, predicted also enkelboot. So okay, so this is working fine for this example, this case. It may happen that sometimes it's not correct, and it's still the accuracy is 670%. So we know that this will not be on the script. So whenever we do, for example, let's try another case. So maybe this, when we run this one, so this will give us new batch. So now this is 6, and this is 3. So this is short. Predicted is dress. So it still flows. Shirt and dress looks like the same. So these are the errors. That's the challenge in the neural network. That's what it is. So this was all about creating a neural network and using a FashionMNIST data set. How does it work? So in the future lesson we'll see some basics behind this one, that, because this is a very long example in which we have covered everything, pretty much everything, but we still not have covered many of the basic fundamental things. So we'll do first those things, and then we'll create a convolution neural network, and we'll do the transfer learning also. So stay tuned. Okay, thank you.